So take it away. All yours.
Thank you. Let me share. Okay. Okay, may I start?
Yeah. Go for it. Go.
Oh, okay. Okay, so welcome back. Good afternoon, everyone, or good night if you are in America, and good morning if you are in Europe. Welcome to the second part on the topic of OH masers and magnetic fields. And I would like to thank the organizers for the opportunity to present this work. I am going to talk about especially of OH masers in low mass evolved stars. And as you may see in this slide, pointer, okay, they can be present at the AGB and the post-AGB and also at the planetary nebula phases together with other masers. This is the list of my principal collaborators in this work, and I would like to thank two particular collaborators that are connected now. Probably one is Malcolm Gray, where we decided to start this working on magnetic fields on planetary nebula especially, and also to Jimmy Green. Thank you. Okay, first I would like to present this HR diagram where you may see the evolutionary track of stars of one solar mass. And this is just to highlight the last stages of evolutionary stage that I am going to be talking about. These are the asymptotic giant branch or AGB phase, the post-AGB, and the planetary nebula phase. The principal motivation to study the evolution of low mass evolved stars is the planetary nebula phase. Thus, as you can see in this gallery of HST images, they present a variety of morphologies, and it's not very well understood which are the factors that are involved in this variety. At previous stages, as you can see in this gallery of AGB stars, as they are observed in this CO transition, especially with ALMA, they may present non-spherical geometries that with some morphological similarities to the planetary nebula. They had been explained by a presence of a binary system towards the center, but there is also another key factor that may influence in the shaping of planetary nebula, and this is the magnetic fields. Okay. This is a schematic view of an AGB star, and these are the typical masers that can be present. First, very close to the central star, the SIO masers, farther away the water masers, and finally the OH masers at the distances of about 10,000 AU. They present this stratification because the different conditions for the pumping of each molecule. This is the typical spectra for the OH masers with a double peak profile that is basically tracing the circumstellar envelope in expansion. During the AGB, there is a typical mass loss rate of about 10 to the minus 4 solar masses per year. This mass loss drops around 3 orders of magnitude at the beginning of the post-AGB phase, where when other phenomena like collimated outflows may appear. And it's at this stage that the masers that are present during the AGB phase starts to disappear in this sequential way. First, the SIO masers, after the water masers at a typical time of 100 years, and finally the OH masers at a time of around 1,000 years. Okay, now let's talk about magnetic fields and polarization. These are the stellar magnetic fields across the HR diagram. For example, for the main sequence and a solar type stars, the values are between 1 and 1,000 Gauss. For stars at the post-main sequence, for example, in the red giant branch, the values are similar between 1 and 1000 Gauss. But for the AGB stars, these values are smaller, between 10 to the minus 3 and only 10 Gauss. As you can see, there are some areas where the values of the magnetic fields are not very well known. And just to remember that the highest magnetic fields are in neutron stars. Regarding to the masers that are present during the AGB phase, these three species, they are related to the magnetic fields. These are the typical densities in the environment where they are present. For example, for the OH maser is from 10 to the 5th to 10 to the 8th particles per cubic centimeter. And this density is increasing towards the center of the star where the SIO masers are located to 10 to the 10, for example. The maser emissions tends to be polarized, and this could be due to unequal population of the submagnetic labels of the molecule, and also due to a magnetic field in the maser region. So the maser emission could be circular or linearly polarized. And for example, for the case of the OH masers, the fraction of circular polarization is usually high and could be 100%, and several tenths of percent of linear polarization. In the case of the water masers, the circular polarization is smaller, even could be smaller than 1%, and a few percent of linear polarization. And for the case of the SIO masers, it's typically several tenths of percent of linear polarization. From this maser, it has been possible to measure the magnitude of the magnetic field as well. For example, in this plot, you can see here the log of the magnetic field strength versus the distance from the AGB surface measured in units of stellar radii. The boxes for each of the maser species represents the typical values that have been measured in the literature mainly from these works. And also these are like the mean values that we can expect. For example, for SIO masers, the values are around 3.5 Gauss. For water masers at distances between 5 and 80 AU, the values are between 0.1 to 0.3 Gauss. And finally, for the OH masers, at the distances between 100 and 1000 AU, the values are between 1 and 10 milligauss. Also here in this plot, you can see different behaviors for the magnetic field that are represented by this linear trend. For example, R to the minus 1 is for a toroidal type magnetic field. R to the minus 2 is for a solar type magnetic field. And R to the minus 3 is for a dipole magnetic field. And as you may see for the observations, they are not enough to constrain the behavior of the magnetic field. Also, there are polarimetric observations toward late AGB stars and also post-AGB stars, and principally towards water fountain sources. The water fountain sources are characterized by water masers that are tracing high velocity jets associated to the source. For example, in this one, where the arrows represent the proper motions of the water masers, and this size of the arrow corresponds to 100 kilometers per second of movement. This is the first water fountain source that was discovered long ago. And it also was the first source, the first water fountain where the magnetic field was measured and also estimated the geometry of the magnetic field by Blemmings and collaborators. These were the results. In this work of Blemmings of 2006, they were able to measure the magnetic field strength in the water masers that are represented by the circles in color that are tracing the outflow that you can see in the other plot. They found a magnitude of around 85 plus minus 33 milligauss from these masers. And they also estimated the orientation of the magnetic field, but that is indicated by these red vectors, that is more or less perpendicular to this line that is representing like the main axis of the outflow or jet. In a few years later, Amiri and collaborators also measured the magnetic field in the water masers, and they found a value of a little bit smaller of 31 plus minus 8 milligauss. And they also were possible to measure the magnetic field strength in the circumstellar envelope that is traced by the OH masers that are represented here by the triangles in blue and red. And they measure a magnetic field of around 100 microgauss. They also, in the years later from this study, they also studied other water fountain sources that present OH masers, and they found similar values of a few hundred of microgauss. Now related with the role of the magnetic field in the shaping of planetary nebula that has been discussed in the field for several years, and it continues to be discussing. During the AGB phase, the magnetic pressure is dynamically important at the AGB stellar surface. At the post-AGB and planetary nebula phase, the magnetic field may play a dominant role in the launching of jets from accretion disks, either around stellar companions, if we consider binary systems towards the center, or a central star. About the maser emission, well, we have seen that we can carry out maser polarization observations, and they have the potential to provide a detailed picture of the magnetic field strength and its configuration all the way from the AGB to the planetary nebula phase, as we are going to see in the following slides. There are some planetary nebula that presents maser emission. If we remember, the time of disappearance for the OH masers after the beginning of the post-AGB phase is around 1,000 years, so then it's expected that they can be present in the youngest planetary nebula. And there is a group of planetary nebula that presents OH masers that was studied back in 1989 by Silstra and collaborators. And several years ago, we did an updated list of these sources, considering only those that present radio continuum emission and OH maser emission in interferometric observations. And we reduced the list only to six sources. There is also a group of planetary nebula that presents water masers, and we think that these water masers are not the remnant of the AGB phase because they are supposed to disappear only in 100 years. So then most probably there are other mechanisms that excite the water masers associated with these sources. Back in 2022, Kala and collaborators found a group of 4 candidates of OH maser emitting planetary nebula, and they are most probably likely to be part of this, let's say, selected group because there are only a few sources. They are very interesting, but it seems that well, the phase is so short and the probability to have masers is not so high that's why this number of sources is very small. Okay, this is just a figure to show how these planetary nebula look like, for example, at radio continuum and infrared wavelengths. Most of them, even those that are observable at the optical wavelengths, present this bipolar morphology. So then most probably these sources that presents maser emission, these planetary nebula, they are characterized by non-spherical mass loss rate. And most probably they pertain to a bipolar type planetary nebula. Okay, this was the first planetary nebula where water masers were detected more than 20 years ago. And they are located towards the center of the radio continuum emission that presents this S shape at 3.6 centimeters. And the water masers are also located at the edge of this structure. And towards the center, there are also present OH masers. These OH masers were studied by Yolanda Gomez and collaborators back in 2009, and they detected this transition at 1665 megahertz. And they also saw this pattern on the B spectra. So this is indicative of possible Zeeman pairs. They were able to determine a magnitude for the magnetic field of around 0.9 milligauss. And they also found a high degree of circular polarization, more than 50%. A few years later from this study, we decided to observe this source again using the Australia Telescope Compact Array, but we were not able to detect the transition at 1665 megahertz, but we do detect the transition at 1612 and the transition at 1720 megahertz. That is also present in other sources, interestingly. We found a high degree of circular polarization of around 72 plus minus 25% in some of the features. But in our case, this is the year of our data. We were not able to find possible Zeeman pairs on the spectra. So we were not able to measure the magnetic field strength. These are the equations that relate the polarization fraction with the Stokes parameters. This is for the circular polarization fraction and the linear polarization fraction, just to know, okay. And simply the presence of circular polarization is intrinsically an evidence of Zeeman splitting, according to this work of Deguchi and Watson, even though it is difficult to identify the classic Zeeman pairs. Also in this planetary nebula, K335, a few years ago, in a work by O and Gao, they were able to find a possible Zeeman pairs in the B spectra of this OH maser transition at 1635 megahertz. They found a high percentage of circular polarization, again, more than 50%, and they were able to estimate the magnetic field between 2.9 and 4.5 milligauss. Going back to this interesting planetary nebula, IRA 16333 minus 4807, we detect back in this year a maser emission towards the center of the planetary nebula. And a few years later, Kiao and collaborators were able to detect OH maser transition. Here I'm just indicating the one in blue in red, the transition at 1720 megahertz. The masers present a structure that is more or less perpendicular to the major axis of the radio continuum emission that could be traced in an outflow associated to this planetary nebula. They propose that these masers may trace short-lived equatorial ejections, considering that this transition is excited by shocks. They also present the circular polarization. In red, we have the left circular polarization, and in blue, the right circular polarization in two different epochs for this transition at 1720 megahertz. And if you see, there is a shift between the two. So this was a very nice result because this was the first planetary nebula where Zeeman pairs are clearly detected. And they determine a magnitude for the magnetic field between 2.7 and 9.7 milligauss. We decided to study two of these planetary nebula in more detail, looking for some variations of the magnetic field in these sources. So we used the Australia Telescope Compact Array using the 6A configuration and a velocity resolution of around 0.1 kilometers per second. We carried out these polarimetric observations back in 2017. And these are the results. Okay, this time we were able to detect the 4 OH maser transitions around 18 centimeters. This is Stokes I in this column and Stokes B for the different frequencies. And we also found a high degree of circular polarization, as you can see for some features, for example, 71 plus minus 18%. If we zoom in into this transition at 1720 on the Stokes B, we see this pattern. And we also, if we observe in detail the circular polarization, the left and right in blue and red, we see again this shift. So then these new spectra do show evidence of Zeeman pairs as in the previous observation of Kiao and collaborators. We estimate a magnitude of the magnetic field between 2 and 11 milligauss. Okay. We also studied this other planetary nebula, IRAS 17393 minus 2727. These are the results. In this case, we detect 3 of the 4 OH maser transitions at 18 centimeters. For example, the transition at 1612 is very intense of around 80 Janskis. And if we compare with previous observations, we found a variability of around 1.2 Janskis per year in this source at this transition. Here you can see also the left and right circular polarization, but in this case, we were not able to identify this shift between the left and the right circular polarization, but we do found this pattern in the Stokes B at this frequency, 1612 megahertz. In this case, we found a smaller circular polarization fraction, but it's significant. It's around 38 plus minus 4%, and a linear polarization of 16 plus minus 2%. If we analyzing in detail this spectra, we were able to estimate a magnitude for the magnetic field between 3 and 20 milligauss for this source. As an additional results, for the source IRAS 16333, for example, we know that the right circular polarization is at the highest frequency than the left circular polarization, especially for these two features. So then the local magnetic field of this component is pointing toward us according to a work of Green and collaborators. And this is the same result as in the observations of Kiao published in 2016. But if we check in detail the feature at this velocity, minus 55.7 kilometers per second, we found that the sense of the magnetic field is reversed, now is away from us. So it seems that the magnetic field appears to have reversed in direction if we compare with the second epoch of observations of Kiao. Regarding the other planetary nebula, we found that the magnetic field strength at 1612 it appears to be consistent with the values reported by Gomez and collaborators in 2016. But we know that from the linear polarization that there is evidence for rotation of the sky plane component of the magnetic field. As a summary, the strength of the magnetic field is quite similar to the previous observations in these two planetary nebula, but it seems that there are changes in the configuration of the magnetic field in both sources. The geometry of the magnetic field is a key to understanding the variety of morphologies observed in planetary nebula. And we are hoping for gas cap OH data that I hope to have. We could have good news tomorrow. I'm hoping to hear that from Joe Dawson, because it is in this survey we may detect much more and a significant number of planetary nebula presenting OH maser emission, and we can study these sources as a group and not only just a few of them, as we have done now. So now I would like to present this as a future work. I just started a collaboration with Laurence Saban. She also studied the magnetic field, but another wavelengths at millimeter and submillimeter wavelengths. For example, to study the dust polarization. and it's able to determine the orientation of the magnetic field at larger distances. This is just an example, for example, for a source that is considered a protoplanetary nebula, that this source is also an OH maser emitting as well as water masers. That is this work published by Lear Ferreira back in 2012. But for example, here you can see in red the orientation of the magnetic field at different resolution and scales related to the distance from the source. You can also see here the beam size, and this is the resolution from different observations with different instruments. This is KARMA, SMA, and ALMA. And for example, here, if we observe in detail the vectors of the magnetic fields, it seems that they present an hourglass structures that I think have also observed in some young stellar objects. So I think it's very important that we were able to talk about these sources that sometimes present similar characteristics, even though it's at the extreme of the evolutionary stages of the stars. And thank you very much for your attention.
Thank you very much. Excuse me. Coming down with something. Thank you very much for your talk. It's a really interesting set of observations. Do we have any questions? Okay, I didn't see any hands shoot up, so I'm going to ask a question. The magnetic field reversal that you mentioned towards the end there. I was wondering if those observations were made with the same instrument.
Oh, yes. Let's see.
Mm.
Yes. In the case of, for example, in this work, for example, I don't remember very well, but it was using the Australia Telescope Compact Array. And this source was identified, I think it was in a survey that they were doing. And luckily, they identified this source presenting OH masers when they study in details the sources that were presented in the survey. So that was done with the compact array, same as our study. So
Oh, that's
it's the
good.
same
Okay. At least
instrument. Yes.
I've always been told that we can trust the ATCO with circular polarization. I wonder, was I know the first one wasn't yours, so maybe you don't know this offhand, but was it a similar was it the same configuration? Like, was it a similar resolution?
I don't remember about that. I have to have a look about that. Yes.
Fair enough.
I think the spectral resolution was not exactly the same, but the configuration I don't remember.
Is there some physical mechanism that would account for a magnetic field reversal, such as what you've observed?
I really don't know. I don't know if Malcolm has some insights about it.
I'd love to hear. Yeah, I'm curious because I love finding things like that in the data. It's like, oh,
Yes.
something's happening, but then yeah, it's like it's somebody else's job to figure out why.
I mean,
Oh, Malcolm,
it
hey, Malcolm.
does seem to be particularly, it's a real thing because one feature is consistent with the previous observations, as I understand it, but like another feature, it's reversed. So, it does seem to be real. I'm not sure I could give you an obvious explanation though.
So cool. Yeah. Well, the theorists can get back to us. Michael?
Yeah. Hi, Lucero. Thank you so much. It was really interesting. So just on this slide, I was wondering, so this is 1720 megahertz OH masers. Are these common in AGB stars? And is that then some shocks from some expanding shells?
Well, in the case of AGV star, I think the most common transition is at 1612 megahertz.
Yeah.
They can be also present the others, but this one is the most common. And for example, this transition at 1720 was not precisely expected on planetary nebula, but
Yeah.
it was detected. And in fact, from this little group of only 6 sources, there are 3 of them that presents this transition. So I think that there are, well, if here there is developing a jet or an collimated outflow associated to the bipolar morphology of the planetary nebula, probably this can be, these shocks may be exciting in some way this transition. I don't
Okay.
know.
Have there
I
been other
suppose.
shock tracers detected for that source? I guess okay.
Mm,
SIO is probably.
mm. Well, regarding to SIO, I know as a colleague that is looking for this emission towards planetary nebula, but it hadn't been detected yet. They haven't
Okay.
found this emission. So it seems that this appears during the evolution from the AGB towards the planetary nebula, and it doesn't
Okay.
appear, seems.
Okay. Cool. Super interesting. Thank you.
Thank you.
I wonder also because the intensity of the 1720 masers seems to be relatively low compared to, some of these big booming masers that we get of tens or even hundreds of Janskis. I wonder if then maybe, because I know a lot of us have in our heads, 1720 maser equals shock. It could just be like you said, if a jet is forming and it's colliding, even though it's maybe not as strongly as we would expect to see perhaps other shock traces like SIO, it still potentially that type of physical condition can certainly lead to 1720 emission, particularly weakly like that. Hmm.
So can I one follow up on this?
Mm.
So is it only detected in 1720 megahertz?
The magnetic field, you mean?
No, just the maser itself. Is it only for the source? Is it only the?
For,
Oh, okay.
no,
They're in
we were
16.
able to detect the 4 transitions.
Oh, okay. I see.
Yes.
Oh,
Okay, thank you.
having another look at that. Is that 1612 feature? Is that kind of one half of the double horned feature? I can see it's a little bit skewed there. It has a bit of a longer tail on the right hand side, the positive velocity side.
Yes.
Yeah. Yeah, 'cause it looks like the 1720 is at quite a different velocity. Not a huge difference, but different enough maybe. Anyway, sorry, Jay, you have a question.
Yeah, thanks, Anita. Hey, Lucero, but that's really
Hi.
awesome talk. Thank you so much. Just one simple question. What was your total integration time per source for the ATCA observations?
That's a good question. I don't remember very well. I think the total integration time on the source, I think there were between 2 or 3 days of 12 hours, but we observed around 3 sources or something like that. So maybe, I
Just
don't know,
that,
maybe
uh,
4 hours, I don't know, per day, considering the overheads. I need to check it.
yeah, and no, it's just that the noise or the sensitivity is really good, and I was just wondering because I'm also dealing with quite a lot of ATCA data, and I was wondering these results, these spectra look really good. Yeah, so thank you.
Yeah, thank you.
Do you have any other questions? Well, I have another question if that's all right. You had a plot, I think, earlier in the talk where you were kind of showing like a schematic of different distances from the center and different magnetic field strengths.
Yes, I know which one it is.
Yeah. Because I think yeah,
This one.
that one, yeah.
Mm-hmm.
So, oh, I see. Okay, okay. I think I misread it originally because in my head I thought it peaked somewhere in the middle, but no, it does seem to be sort of dropping off with the SIO in the
Yes.
middle and the H. Okay, okay, never mind. Okay. Do we have any more questions?
Feedback. We are preparing the draft now. So.
Well, yeah. So I think that, well, as far as I'm concerned, I think the message is that these are very different objects from AGB stars, and you shouldn't sort of rely on that sort of plot for the planetary nebulae, right? They've
Yes.
got a very different structure.
Mm-hmm.
Even though they're
That's
just
right.
later evolution of the same sort of object, but they're really very, very different.
I wonder if that magnetic field reversal would be apparent in any of these other tracers. That would potentially be interesting because then if it was some kind of a global phenomenon, which maybe that's not realistic, I don't know. As opposed to that being sort of a micro field, rather than a global phenomenon.
Well, if we looked at the water, maybe that so like the Fleming's observations, it seems to sort of corkscrew. So we see in another spectral component that there seems to be a rotation of the sky plane linear. So you can sort of see maybe this thing is rotating. Now the a reversal in the line of sight component seems harder to understand, but maybe the way the whole thing is corkscrewing, depending on the angle you're looking at it, it might be due to that. So you can actually sort of see stuff moving over a timescale of several years as it follows this sort of spiral pattern. So I'm trying to do the time scales in my head, and I'm getting nowhere. It's very early in the morning here. But yeah, the idea that all this stuff is corkscrewing is probably the way to go.
I suppose gas cap OH is going to be a really profound step in terms of these kind of regions, because if these are relatively small, right? Because I saw a picture there where you're looking almost on the scale of oh well, this here, for what's that, 500 AU? Oh, that's not that's small. But yeah, with the improved resolution over previous studies, it'd be really interesting to see, what can come from that, and if we can attribute more of these features to individual regions rather than, the huge beams of previous OH surveys. Oh, cool. Do we have any other questions?
Well, again, so just thinking about that, actually, with the sort of scales it got there, I think over just a few years, you wouldn't. Well, looking at where the OH masers are on there, that I think it's not going to go all the way around in that sort of time at the velocities we've got. So need to find yet another explanation, I think, for the reversal.
What was the magnitude of the change in the magnetic field? Because if it's switched, was it sort of, I don't remember the numbers that you put there. Was it a few milligauss in one direction, then a few milligauss in the other, or was it tens of gauss?
Yes, it's a few milligauss.
Few milligauss, yeah.
Yes. So this one. This one.
Got some hands up. Max?
Yeah, well, just thinking about it, wanted to check whether the same software was used for like both epochs, just in case there is some strange bug somewhere which we don't understand. It's very unlikely given that it's two polarizations, but in general, comparing two different epochs processed differently might have its own dangers unrelated to astronomy. In particular, actually, velocities, when similar to what we talked about in the previous session, because basically the models in software commonly in use were not verified down to the level we typically work at. I tried to guess from the plots and kind of think that it's probably not the case here, but it's always nice to use identical versions of the software when, say, different epochs are processed and compared.
Okay.
Jay?
Yeah, thanks, Anita. Sorry, I just noticed something, and I might be completely wrong on this. Can we go back to your water major internal motion map, if we can?
This one?
Yeah, yeah.
Ah.
The size of the arrows with 100 kilometers per second. Are we? I mean, again, I might be completely wrong here. Is it 100 kilometers per second or milliarc seconds? And is the units are all right? Like because you down bottom the color scale represents the VLSR. So when you say 100 kilometers per second, so the arrow length, so it's going from -65 per se to +65 or something, if arrow length is that much.
Yes, this is the velocity along the line of sight that is from -55 to 130. So almost 200 kilometers per second is the velocity dispersion in the spectra. And the arrows represents the magnitude of the proper motion of the water masers in the plane of the sky. So a size like this one represents a proper motion of 100 kilometers per second. So you measure in milliards seconds, let's say, per year. And then you transform the distance, considering the distance to the source, then you change it to kilometers per second.
Cool. Yeah, that makes more sense. Yeah, I was just more used to see them in milliarc seconds per year.
Milliards seconds per year, that's why.
Yeah, cool. Cheers.
Yes.
Yeah, thank you so much. Cheers.
You're welcome.
Any more questions or comments?
Yeah, sorry. Can you just remind me what the speeds are for the OH? So
Yes.
are we anywhere near that sort of 100?
This or this one?
Oh right, yeah. So the range is covering
I think this
for the
is minus.
1720. There's at least 40 kilometers a second or something like that. Yeah.
Yes.
Would you expect the water masers to be traveling out faster because they're a little bit closer to the middle?
Yes, I think that's right, because they seem to follow this sort of narrower jet, and they're further out.
Mm.
So it's stuff that's been accelerated more.
Interesting. I have a lot of this kind of stuff in my data set.
That's again a sort of it's opposite to what you see in AGB stars. So you've got I mean they're the DOH is the furthest out, but in the planetary nebulae it seems to be the water that's further out.
Yes.
Oh, cool. Oh, Pusava?
Yes. I was wondering whether, observing this with the source with VLBI, so you might know which maser you actually seen, because OH maser from the Wouter paper, the OH maser is not only one spot, right? There are quite a few feature there. If you go
Yes,
back,
that's right.
yeah,
Sorry. Here, yes.
yeah, exactly. And how variable is the OH maser in planetary nebula? For example, with the the field reversal, maybe we see different maser. For example, if you go back to the one with the spiral with the model of the magnetic field in earlier slide. Yeah. For example, I think the red, that's the OH, right? The triangle. Yeah.
Yes, the triangles are the OH, yes.
Yeah. And if the model of this spiral magnetic field, if we see the triangle on the top, so we might see the field come towards us, and then if we see the triangle at the bottom become brighter, maybe that epoch you actually see the maser at the bottom, or not? Right. That
I don't know about this data. I haven't checked it in detail.
Yeah. No, just example, mapping the the maser may help to explain at least for one epoch, and in the future, if we observe it again, whether it's agree. So I'm not sure about this variability of each maser cluster or maser clump in planetary nebula.
Okay, thank you for your suggestion. Thank you.
It's yet another justification for having interferometric monitoring. There's so many questions that seem like they could be answered by, well, it might be in a different spot, or verifying that it's the same spot it becomes so valuable, particularly with these magnetic field studies. So
Yes.
how else are we supposed to match up Zeeman pairs? Yeah.
Yes.
Well, it's really interesting work. Thank you so much. Thank you again for sharing.
Thank you. Thank you for the invitation.
No worries. And thank you to everybody who participated in the discussion, and thank you to everybody else who attended. This has been really interesting studying, learning, because I'm new to all this magnetic field stuff. I know I've been getting a lot out of this. So yeah, if we want to, I added everybody in here who's already been on Slack. I added you guys onto the Slack channel for this session. So if you have any other clarification or questions or discussion points, feel free to take it over there. And yeah, that's it, I suppose. And we'll see you guys all in the next session, hopefully. So
Okay,
take care, everyone.
Yep. See you later.
Bye.
Yep.
Yeah.
Bye. Bye.